In this section of chapter 2, we will talk about Dalton's theory, metals, nonmetals, and metalloids. Now, Dalton was the first scientist to point out that every element is made up of tiny atoms, and all atoms of a given compound are identical. So I'm underlining that. So for example, if I have atoms of iron, no matter from which iron compound I get iron, Fe, is going to be identical. There'll be no difference in property, in mass. So all those would be identical. On the other hand, it's going to be different from another atom. For example, atom of neon or hydrogen or say calcium. Atoms of an element are not changed into atoms of a different element by chemical reaction. In other words, chemical reaction would neither destroy an atom nor create an atom. So that's law of conservation of mass. That's why many of you heard about balancing of a reaction. By balancing, we make sure that we haven't destroyed any atom nor created any atom. If I have one carbon and oxygen molecule reacting, I get carbon dioxide. If you look at the reaction, I begin with one carbon, end up with one carbon, begin with two oxygen, end up with two oxygen, and I haven't destroyed carbon or oxygen. Just it is in a different form as it forms products, because carbon dioxide, is a gas, is different from carbon, solid carbon, or gaseous oxygen. Compounds are formed when atoms of more than one element combine, and that's what you see here. Carbon plus oxygen gives carbon dioxide. Hydrogen and oxygen gives H2O. Now scientists are always curious. They wanted to know, once they heard from Dalton that every substance is made up of tiny building block or atoms, then they wanted to know what makes an atom. In other words, they wanted to do experiments to find out what is inside of an atom. It's like kids often have curiosity. They want to know what is inside of an egg. If you have a kid and let the kid play with an egg, you know what the kid is going to do. The most common observation would be the kid is going to drop the egg because he or she is curious to know what is inside of an egg. Similarly, scientists, in order to understand what is inside of an atom, in their experiments, they wanted to break an atom and find out what is inside of an atom. These experiments by scientists find out that an atom has electron, which is negatively charged, proton, that's positively charged, neutron, that doesn't have any charge. On the mass side, electron is much lighter than mass of a proton or a neutron, which is about 1/1837 mass of a proton or a neutron. Here we wrote down proton and neutron approximately as 1, even though there is a small difference in their masses. So for most cases, we can consider them to be equal in mass. Protons and neutrons have unit mass, and electron mass is much smaller, which is 1/1837 mass of a proton or a neutron. Now these are in atomic mass unit, and just to show you the conversion factor, one atomic mass unit is 1.66 times 10 to the negative 24 gram. Now I already mentioned this law of conservation of mass. Total mass of substances present at the end of a chemical reaction is the same as the mass of substances present before the reaction takes place. Now scientists did all these kind of experiments, different types of experiments, to find out what comes out of an element or an atom. Now, one of their experiments they did was with cathode tube, and which we are seeing in that picture. Under high voltage, these electrons or negatively charged particles come out from one end and it goes towards the other end. And J.J. Thomson made this discovery, and those fine negatively charged particles were later were tested, and they're known to be electrons. Now, Thomson not only stopped in identifying negatively charged particles as electrons, he also found out charge over mass ratio of an electron. So he got 1.76 times 10 to the power 8. Of course, he wanted to know charge as well as mass, but unfortunately he could not quite get that, so he just got the ratio. But that was very useful during his time. Now, Millikan oil drop experiment is very well known, and this I briefly describe this experiment, and that helps us to know the charge of an electron as well as mass of an electron. In this case, if you look at the right hand side, there is a atomizer, we call it. It basically allows droplets, small droplets of oil to go into the chamber, and because of the gravity, these droplets would come down. Now, as these droplets go down, as you can see here, the red droplets which are shown in here. Now, there is a source of X-ray. You can see right bottom there in this, there's a source of X-ray. X-rays pass through the chamber. What X-ray does is it knocks off electron from air molecules, and then those electrons will be floating all around. And as the droplets come down because of gravity, now some of these electrons would be landing onto the oil droplets. The question is, what are the possibilities? The possibility is a particular droplet may have no electron at all landing on it, or may have one electron, may have two electrons, may have three electrons. So in other words, you'd expect some multiple number of negative charges landing onto oil droplet. Now, by knowing the velocity of these oil droplets, because as these oil droplets come down, you can see that there is a positive and negatively charged plates. When oil droplets are negatively charged, they'd be attracted towards positive. So since the positive plate, let me point out, this is the positive plate with an arrow I'm showing you. The oil droplets would be attracted to that positive plate. And so in other words, it would be falling down rather more slowly, because gravity is pulling it downward, but electrostatic attractive force is pulling it upward. So in some cases, depending upon net force on the oil droplet, some of them would be going towards the positive plate, some of them would come down rather slowly, and some of them, without having any electron on it, would come down just as if there's no other interaction other than gravity. So by knowing this velocity of these electrons, Millikan figured out the charges on these oil droplets and also charges of electron. Now here we're showing you, again more explicitly, oil droplet with one electron would have -1, with two droplets would get -2, and as you can see, these oil droplets are coming down at different rates, and by knowing the rates, Millikan eventually found out charge of an electron is 1.60 times 10 to the negative 19 coulomb, and mass is 9.10 times 10 to the negative 28 gram. Next, we're going to talk about radioactivity. In Chem 112, we discussed that in more details. Radioactivity is the spontaneous emission of radiation by an atom. especially some of the bigger atoms. As you go beyond lead, all those elements are radioactive. That means they would spontaneously break down with the emission of some radiations. So scientists in earlier years, when they discovered radioisotopes or radioactive substances, they tried to find out what is really coming out of a nucleus, because in those days, as I said, that scientists were always curious to break down an atom to find out what is inside of an atom. In radioactive substances, naturally they break down. So that's why it gave scientists an opportunity to find out what is coming out of a nucleus. And that's how they knew that a central nucleus has protons and neutrons. Rutherford, by working with radioactive substances, discovered three types of particles that are coming out of radioactive nuclei. What he basically found out that from radioactive substance, when the radiation or beam is coming out, it appears to be a single beam, but as it passes through positive and negative plate, it's split into three different beams. And from his analysis, we know that one of these radiation beam is attracted towards positive plate, and obviously it must carry a negative charge. The other one remained undeflected. It went along the direction in which the original beam was coming. And the other one, the third one, is attracted towards negative plate. So it must contain a positive charge and is called alpha radiation or alpha particle that makes up that ray. Now later on, beta rays were identified nothing but electrons. And then the one which was not deflected at all is known to be gamma rays. Often these gamma rays are used for cancer treatment. So make sure you probably heard about this name before. And alpha radiations or alpha rays are made up of alpha particles or helium nucleus. So if you get rid of electrons from helium, that would be really same as alpha particle. At this point, scientists knew that every atom is made up of protons, neutrons, and electrons. But the question is, how are they together? Are proton, neutron, electron all together in a small volume, or are they all scattered all over the atom? So with this kind of question in mind, Rutherford did additional experiments, and he used thin gold plate or thin gold foil. You know that gold plate is just like any other substance. It has atoms, it has nucleus, and all those things. What he did is he allowed alpha particles to strike the thin gold plate. So he pretty much used alpha particle as a bullet to strike the gold foil, because he wanted to know what happens after these alpha particles strike the gold plate. He was very shocked to see the final results. He found that most of the alpha particles passed through undeflected. Only few of them went backward. Now that was puzzling because he didn't quite expect that. Now he explained that finding by saying that nucleus is most massive in an atom. So obviously protons and neutrons are the most massive among all these three particles. So you can say that nucleus, which is made up of protons, neutrons, and that's the most massive part, and electrons would surround the nucleus. Now how can we then explain that most of the alpha particles went through undeflected? Let me show you that. If alpha particle is heading along this direction, you know that alpha particle is much more massive than an electron. So alpha particle is nothing but helium nucleus with 2 charge and 4 masses. So as it passes through, and if electrons are around it, it's not going to be stopped by electrons because electrons are so light, and I have mentioned that to you before. So as alpha particle goes through this along this direction, it would go through undeflected because there is no massive particle to stop it. Just like you're throwing a ball at, if there is a wall, the ball is going to strike the wall and go backward. Why? Because the wall is quite massive, and that's why the ball bounces back. On the other hand, if there is no wall, ball would just keep on moving along the direction you have thrown it. Same is the case with alpha particle. If it doesn't experience any massive object along its way, it would go through undeflected. So that's why most of these alpha particles go through undeflected. And the question is why a few of them go backward? Because they experience the massive nucleus, and then those would go backward. So this is how Rutherford explained how these protons, neutrons, and electrons together. So protons and neutrons are within the very small volume of a nucleus, and electrons are outside of the nucleus. Well, scientists always had a suspicion that electron cannot be within the nucleus, because if it is within the nucleus, there will be a strong attraction between proton and electron, and you can't get rid of that electron. But we know from simple experiments, because of the very fact of having a static, like if you rub your hands, it becomes a static. Why? Because you move electron from one hand to the other hand, so it gets positive or negative charge, and that causes static. Because this tells us that by simply rubbing, you can move electron. That means electrons are not strongly bonded, so that's why electron cannot be within the nucleus. It has to be outside of the nucleus and much less strongly bonded. Now, we already mentioned this. Now this picture again is showing you the same thing, why most of the alpha particles go through undeflected. Based on the experiments that I have just mentioned, Rutherford concluded that the nucleus is pretty small but quite massive, and it having the massive protons and neutrons. Of course, this is in comparison with electron. And electrons have very little mass, and it is moving outside of an atom, outside of the nucleus. Keep in mind that electrons cannot be static outside of a nucleus, because if it is static, then force of attraction would bring that electron close to the nucleus. And that's why, we know from physics that if this is the nucleus, if it's the electron, it cannot just sit there. It has to move, so that there is a force, centrifugal force, that would balance the attractive force inward. And the other thing is, most of the volume of an atom is basically empty space. We know that there are electrons, but those are such a small mass that it doesn't cause alpha particles to go backward. Now here we are going to review everything. Protons and electrons are the particles that have a charge. Protons and neutrons have essentially the same mass. We call unit mass in atomic mass unit system, which is close to 1. We round it off. But there is a small difference that you see in that table. The neutron is slightly more massive, but again it's very close to 1. The mass of electron is so small that in many cases we just ignore that mass. Now this is how we represent symbol of elements. First we write down the symbol of elements, this C for carbon, and 6, the bottom number, represents number of protons in the nucleus, and which you can get from periodic table. In periodic table, elements are organized in increasing number of protons or atomic number. The top number is the number of protons plus neutrons for a particular isotope. There's different types of carbon, but in each case, whenever you are dealing with carbon, you have 6 protons. So you can have 6, 13. That means I have 6 protons, 7 neutrons. So keep that in mind. The top number varies depending upon what kind of isotope you have. Periodic table gives the mass, an average mass of all the isotopes. Now, again, here you're looking at different isotopes of carbon, carbon 11, 12, 13, 14. So you can see here how you can see here the number of protons is the same because we are all dealing with carbon. As long as we're dealing with carbon, number of proton has to be 6. Number of neutrons, again, that determines the overall charge because it has to be added to number of protons. So 6 plus 5 gives 11, 6 plus 6 gives 12. So that's how we determine the total mass, and from total mass we find out how many neutrons are there. If it's neutral, number of proton has to be balanced by number of electrons. So that's why in this case you see you have 6 electrons for each of these carbon because we're dealing with neutral carbon atom. Now the question is, how do I know the mass, atomic mass of a substance? So if you have a gaseous sample, you basically let it pass through what we call mass spectrometer. As the gaseous sample passes through, it is ionized. So as it ionized, it passes through a magnetic field. So when it passes through magnetic field, it interacts with that magnet, and depending upon the mass, the beam that shows 1 before it passes through the magnet would be now split into different beams depending upon their masses. Then you tune in different masses and see what kind of signal you have. If there is no signal, that means that particular mass is not present. Say if you set your mass as at 35. If you see a large signal, that means mass 35 is present in significant quantity. If there is a small signal, that means there is a smaller quantity of that mass. So this is how you find out atomic mass and their abundance in the sample. Now, since in the real world we deal with large amounts of sample, atoms and molecules, always we use average masses. And average mass is calculated from the isotopes of an element and their natural abundance. And we're going to do problems on that. So at that point you'd understand it better, that how average mass is calculated. Periodic table has the average mass. In this slide, you're looking at the formula by using which we can calculate average mass of an element. P1, P2, P3, these are percent abundance of different isotopes of that element. Remember, I mentioned that some of these isotopes are more abundant than the other ones. For example, in case of carbon, carbon 12 is most dominant, but carbon 11, carbon 13, they're not present in that large quantity. So that has to be considered in calculating the average. So that's why we need to include percent abundance times the mass of that particular isotope. And that's how you calculate the average mass. And that average mass is shown in periodic table right underneath the element. Now, at the bottom, you're looking at a typical mass spectrum. Of course, this is hand-drawn, so it would not be to the scale. But you can see in this particular case, when you tune in mass 1, you see a big signal for a sample. For mass 2, you get a smaller signal. Mass 3, you got another signal. So if I want to interpret this mass, I would say that I have a much larger quantity of mass 1 in my sample and smaller quantities of mass 2 and mass 3. Here we are looking at a periodic table in which elements are organized according to increasing atomic number or number of protons. The number on the top you see 1, 2, 1 on the top of hydrogen tells us that there is 1 proton. On the top of helium is 2, on the lithium is 3, beryllium is 4, and those are nothing but number of protons. Now, in periodic table, if you go vertically downward, you're going through a group, and a group of elements have a lot of properties in common. They behave similarly in chemical reactions. So group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A is noble gases. So those are groups. If you go horizontally, that's called period of elements. So period 1 has hydrogen and helium. 2 has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So that's how it goes. In addition to that, you can by looking at periodic table, you can quickly find out which ones are metals, which ones are non-metals, and which ones are metalloids. Metalloids have properties in between. So most of the elements are metals, which is on the left-hand side of metalloids. Metalloids are shown with a different color. You can see in the borderline. Let me show you the corner. So metalloids, these are all metalloids. Boron, silicon, so if you go like this in a diagonal manner, these are all metalloids. So boron, silicon, germanium, arsenic, antimony, and tellurium. Make sure you know these names, at least first 54 names of elements. And as you do more and more problem, you know most of those elements. Even beyond that, there are some common elements beyond that also you need to know, like lead is Pb, for example. So metals are on the left hand side of that borderline elements, and metals are usually shiny, and we'll talk about these properties in just a short amount of time. Non-metals are on the right side, and metalloids are the borderline elements. Now some of the groups of elements have special names attached to it. Alkali metals, group 1A. Metals are called alkali metals, like lithium, sodium, potassium. These are alkali metals. Alkaline earth metals are beryllium, magnesium. This is group 2A, which is the second column. Group 7A, elements are called halogens, fluorine, chlorine, bromine, iodine. 8A, noble gases, helium, neon, argon, krypton, xenon. These are noble gases. They don't react with, most of the time they're non-reactive. They don't react with most of the substances. Then 3B to 2B, 3B, 4B, 5B, all the way go to 2B. Those are called transition elements. Normally they give colored products with other substances. Scandium, titanium, vanadium, chromium, these are transition elements. Again, we're reviewing this, what we already mentioned. The metals are shiny, good conductors of heat and electricity. They're malleable. That means you can bend a metal, it's not going to crack. Non-metals, from the name you know, I underline non. It is just the opposite of metals. Metals are shiny, non-metals are dull. Metals are good conductor of heat and electricity. Most non-metals are bad conductors of heat and electricity. Metals you can bend, it's not going to crack, but non-metals would crack. Metalloids have properties in between. That means it's neither shiny nor dull. It's neither a good conductor nor a bad conductor. So that's why they're called metalloids.